more recent results and recent topics. The first one, I want to talk a bit about our results on how we use modern observations to learn more about convection. And it's motivated not just learning about convection, but actually what does it tell us about how we should parameterize convection. So that's perhaps the twist on lots of literature using observations to look at convection, right? And they all do different things. But what we were focusing on here, we'll be focusing on in this lecture, is how could we use the observations to learn more about parametrization of convection. To learn more about parametrization of convection. So, whilst I'm giving the talk, this work that I'm presenting has been done by a large number of people who are all listed here. Okay, so lots and lots of people have done lots and lots of work. So most of what's in this talk is the work that we've done in my group. So it's not a big overview about everything that has been done, but really recent work, last 3 or 4 years or so, as to what we've been doing to use observations. And I'll split this into 2 parts. The first part is to look at satellite observations. And specifically, what we have been specializing in is try and use cloud observations rather than rainfall observations. So a lot of times, if you use satellites to look at convection, people use OLR as a variable to identify where convection is and what it does. Other people use rainfall from satellites, derived satellites. And we are doing something different. We are saying, can we use the observations of the cloud field to say something about convection, right? And what would that then tell us? Because convection makes clouds, and it turns out there are very specific types of clouds associated with specific types of convection. And if we can identify those, we can learn something. Okay? And then the second part, we'll talk about radar observations, how we've used radar observations to find out a few interesting and curious things that we didn't know about convection. All right, let's start with the satellites. I've showed you this before, but the idea we are following is this. We use a data set called ISCCP. It's the International Satellite, CC, there's a typo there, ISCCP, the International Satellite Cloud Climatology Project. And there's a huge amount of information in that data set. It starts in 1983, goes to 2009. They're reprocessing the whole data set. They will go to 2015, 2016, so it's becoming better and longer, but all the work I'm showing you is from the old data set. And one of the things that's in the data set is this funky histogram, which we looked at before, and it's a bit difficult to understand, but I tell you how it works. So it works very simply. You take a grid box, and there's lots of satellite pixels in the grid box, and you collect all the pixels in that grid box for 3 hours. So you use geostationary satellites and polar orbiting satellites. You just find all the pixels in a 3-hour interval. And then for each pixel you find out where's the cloud top. They do that from the IR temperature, and estimate the cloud top pressure. And how thick is the cloud optically? So they derive that from the albedo, which they derive from solar radiation. So it only works during the day. Okay, that's a limitation. And so then we make 6 classes of optical thickness and 7 classes of cloud top pressure. And each pixel will fall into one of those classes, right? Every time you have a pixel, it will have those 2 numbers, so it will fall into one of those classes. And then what you do is you count how many pixels do you have in each of the classes. Okay? And that gives you a 2-dimensional histogram, basically, of the distribution of cloud top pressure and optical thickness. And you get one of those at every grid box every 3 hours for 25 years. So that's a huge amount of information, and it's very hard to digest it. So what we do then is we apply a cluster algorithm to find common patterns in that histogram. And that's the result of doing that. So in the tropics, or we call it the extended tropics, 35 north to 35 south, we find 8 patterns that seem to be recurring, right? It's nature seems to make 8 types of cloud patterns that are, at this point in time, that's all they are, cloud patterns. We haven't looked, and I'll show you that they will become very useful. And here they are. So the first one here is going to be important, and I showed you this in the lecture on the first day when we talked about organized convection. This one represents organized convection. And it does so. So the colors is just the frequency of occurrence or the coverage in the grid box with pixels of certain combinations, right? So where it's red, we have lots of pixels. So this type of cloud pattern has lots of pixels which have tops high up in the atmosphere and that are very, very thick. All right. This is not just convection. This is lots of stratiform clouds that are very, very thick. Because convection really, as I will show you from the radar data, covers only a very small part. These grid boxes are 2.5 by 2.5 degrees, so say 250 by 250 kilometers. So they're large boxes. And convection in that box really only covers a few percent of the box. Most of what we're seeing here is stratiform clouds. All right, so we know that in the atmosphere, if there's a lot of stratiform clouds associated with convection in the tropics, the convection is likely organized. Right? That's what makes the big stratiform clouds. The next type you can see has lots of clouds that are high up in the atmosphere, but they are thin. And then in the thick part, where you would expect convective clouds and big anvils, there's actually a little bit of coverage, but not a lot. So that's a convection that is not organized. So you have individual convective plumes that make cirrus clouds that are very thin, but there's no mesoscale circulation associated with them, so that they stay thin. There's not much of stratiform cloud. Then we have a regime that looks rather mixed and has some high coverage with mid-level top clouds, so more like congestus clouds, so we call that the mixed regime. We have one that has very many very thin cirrus clouds here. And then we have 4 regimes that have no clouds in the upper troposphere, or very few, and mostly have their clouds in the lower atmosphere, and those are low-level regimes. Now, the first thing you can do is you can ask, where do these regimes occur? So you print the frequency of occurrence of each of those regimes. So where do they occur? So you can see this is a very rare regime. Its overall frequency of occurrence is only 6 or 7%, but it occurs in the ITCZ mostly. Right? It's really where most of the rainfall in the tropics is found. Whereas the thinner cirrus regimes, those two, have a much broader pattern, so they're not confined to the convergence zones. They're much more widespread. You can see they are still in the convective regions, but they spread much further out. So that tells you that the cirrus from convection is sort of flowing out from the ITCZ and is covering large regions. So if you use OLR, this could be a problem because you still count this as strong convection because the OLR is still low. But it's not, because it's really this one where most of the rain, as I'll show you. And then these 4 low cloud regimes, you find them where you would expect them. This regime is a trade cumulus regime. The total cloud cover is very low, but the frequency of occurrence is very high. So if you look at the trade cumulus regions, you get trade cumulus every time, every day, all the time. Right? So very high frequency of occurrence. It also includes clear sky regimes, which is why the Sahara comes out in this regime. And then the other 3 are really stratocumulus type regimes, which we won't worry about too much. All right. Sorry?
There is no particular season. It's just daytime but whole year.
That's the whole year for 25 years. So it's just a climatology. So there's no seasonal. You can split this up into seasons and so on and so on. So we found this a very useful tool to look at how convection behaves. The first thing we needed to convince ourselves is really that one of those regimes is an organized regime, right? And I've shown you this before because you asked me about it, so I brought up these slides before. So this is what we think is the organized convective regime. Occurs about 7% of the time. But the number up here tells you how much of the rainfall in the tropics is it producing, and it's producing 45%. So 45% of the rain comes from a very rare regime. So it's a very important regime for rainfall.
Is it because it lasts very long?
It's because it lasts very long, but it's also because it has a large spatial extent. And so we measure rainfall. We'll come back to that in the radar part. We measure rainfall as an area mean over the box, right? And to make a large area mean, small blobs of convection won't help. Well, it's where it's raining a lot, but if they don't cover much of the area, you won't get much rain in an area mean sense. But if you have these big stratiform clouds, they rain everywhere. Not as hard as the convective ones, but they rain over large areas. So that brings up the area average quite dramatically. We will see that later in the lecture. Okay, hang in there. So one of the things we're seeing, and I showed you this before, is this tells you how often when this regime occurs, how often is the rainfall greater than, how often is it raining? How often is it raining more than 1 millimeter a day, and how often is it raining more than 10 millimeters a day, so heavy rain. And you can see 80% of the time, this regime rains more than 10 millimeters a day. So whenever it occurs, it rains a lot. And this one tells you that more than half of that rain is stratiform. Okay, so we really think this is an organized convective regime. This figure you haven't seen yet. Here we are asking how much does the rain that we are observing comes from each regime as a function of humidity. This is a very interesting curve that has been drawn by many people. And what it shows you is, if you forget about the colors and just look at the x-axis, is how moist is the atmosphere. It's called the saturation fraction. It's the vertically integrated humidity divided by the vertically integrated saturation humidity. Okay, so it's kind of a vertically integrated relative humidity, but it's not the same as vertically integrating relative humidity. But it's a representation of how moist is the atmosphere, how close to saturation. And one of the fascinating things in the tropics is that if the atmosphere in the vertical integrated sense is dry, it doesn't rain. All right, so that's maybe not too surprising. And then there's a particular point somewhere between 0.5 and 0.6 of that measure where it starts to rain, and then the rain increases exponentially with this saturation fraction. All right, so that's a well-known graph. So now we ask the question, how much of the rainfall in each of those classes comes from which regime? All right, and this is the absolute on the left, but it's a bit hard to interpret. So to help us interpret it, we put this on the right here. And that is when it rains, how much comes from which regime. Okay, so you can see it doesn't rain very often when it's dry, but when it rains, it actually comes from the CC, from these sort of non-organized regimes. But if you go to higher and higher humidity, more and more of the rain comes from the organized convection, and by the time you get to very high, very moist atmospheres, 80% of the rainfall comes from this organized regime. Right? You have to put this in context with this, that the high rainfall events are all in the moist part. So this is just sort of trying to connect rainfall to these cloud regimes. Okay? Another thing we can connect to these cloud regimes is we can ask, so what is the atmospheric state when this cloud regime occurs? And we do that here, so that's kind of cool as well. So that helps us understand under what circumstances do we expect organized convection versus non-organized convection. So here are four regimes. This is the suppressed regime. This is the organized regime. These two are the non-organized regimes. Okay. So what's on the graph? The horizontal axis is a measure of stability or instability of the atmosphere. We use something called the K index, but you could use K, but the K index is simpler to calculate from things like reanalysis data. So we use that. And if it's positive, the atmosphere is very unstable, and the more positive it is, the more unstable it is. And if it's negative, the atmosphere is stable. Okay. On the y-axis, we have vertical motion. If it's positive, it's downward because it's in pressure coordinates. If it's negative, it's upward. So we flip the axis here. So up is upward and down is downward. And then the color of the points is the saturation ratio, the thing we saw on the x-axis. So how moist is the atmosphere? And blue means it's very moist, and red means it's very dry. Okay, so you can see in the organized convective regime happens when the atmosphere is really, really unstable. It happens mostly under large scale ascent, so we have very we are in the active parts of MJOs, monsoons, cyclones, and so on and so forth. And the atmosphere is very moist. In fact, it's 0.8 on average. That's when that's happening. If you look at the unorganized regime, what we see is that actually the stability is slightly less unstable, but still quite unstable. It's drier. The atmosphere is quite a bit drier, as we can see here. There's sort of stuff coming out this way, and the ascent is weaker when that regime occurs. Oops, that's not what I wanted to do yet. If you go to the to this regime, which is this sort of mixed regime with more congestus type clouds occurring, now you see the atmosphere is actually near zero on average in its vertical motion. It can be up or down. Can be quite dry, and it can be quite stable when we find these congestus clouds. Then when you go to the really suppressed regime, which is the trade cumulus regime, the atmosphere is really dry. It's mostly stable, can be a little bit unstable, and it's quite dry, and the vertical motion is actually downward. So you can act, but just remember this is quite remarkable because the regimes themselves are just cloud patterns, So all we're doing is we're saying by identifying the cloud patterns, we can say something about the state of convection in the atmosphere. So that's very useful, and we can play lots of games with that. I already showed you this graph. So one of the things we did with this is we showed that the total change in rainfall from the late 90s to about 2010, as we had the data for ISKIP only until 2010, is dominated by a change in the frequency of occurrence in this organized regime. So the largest contribution to the rainfall trend comes from an increased frequency of occurrence of rainfall in organized convection, not from a change in the intensity of the rain, which is counter many studies that are saying rainfall is increasing because it gets more intense. So we didn't find this at all in the tropics. In the tropics, what we found is the rainfall got more frequent, and it's the heavy regime that got more frequent, and therefore the overall rainfall goes up. Not that any of the regimes got particularly more intense. So the intensity contribution is this one, and you see, if anything, the intensity has negatively contributed in the regions where rainfall went down. Okay? A very intriguing one that I wanted to show you is this is the frequency on the y-axis, is the frequency of occurrence of this organized convection, right? Each crosses a year. Actually, it might even be, each crosses might even be a month. Is it too many crosses for it to be years? So each cross is a month in a particular year, and the color tells you which year it is. And this is the global mean surface temperature that month. Just the global mean temperature. One of the remarkable things that we are seeing is that there's an increase in the frequency of occurrence with global mean temperature. So this is interesting because there's several hypotheses around at the moment that the degree of convective organization may depend on the mean temperature of the planet. So a warmer planet may make more organized convection, and we seem to be seeing this in our observation. Okay, so this is another. So the point here is, the point of this part of the talk is to basically make you aware there are these satellite observations, and there's better things to use these days to think about convection than OLR. Right? OLR and rainfall are the typical ones that people use, but we have more insightful information, for instance, from these cloud signatures. Right? That's the morale of this part of my lecture. Okay, now we're going to look at what can we learn about convection from radar observations. Oh, so the other thing we learned from this, which is actually going to become important this afternoon, is there's a strong relationship with the way convection works and vertical motion in the atmosphere. Okay, so we'll come back to that. It's a slightly difficult topic, a controversial topic, but we'll come back to that in the afternoon. More so than with stability. Actually, I'll show you some radar observations. So let's look at some radar observations. Let me tell you a little bit about what we use. So we have in radar in Darwin, which is in tropical Australia, it's about 12 degrees south. We have a research radar. Looks a bit like a God's golf ball, I like to call it, right? So it's like a golf ball, or but it's on a T, and so this is what it looks like. Its wavelength is 5 centimeters, so it really aims at detecting raindrops, not cloud drops. Okay, so we're seeing mostly raindrops. We will be using in our study here a range of about 150 kilometers. It makes a 3D scan of the atmosphere every 10 minutes. We construct sort of horizontal planes, which the radar enthusiasts know are called cappies, but it doesn't matter for most of us. It's horizontal plane information every half kilometer in the atmosphere at 2.5 by 2.5 kilometer resolution. So each pixel you can look at is 2.5 kilometers wide. As you go closer to the radar, you can make 1 kilometer pixels, but we haven't done this in the studies that I'm using. We will mostly use a quantity called reflectivity, which tells you sort of how much return did you get from the volume that the radar beam was shooting at. But we have looked at microphysical parameters too, but I won't talk about them here. There's an algorithm, for those of you who work with radars, it's called the Steiner algorithm. For those of you who don't work with radars, don't worry about it. The algorithm can identify whether a pixel has convective rain, stratiform rain, or no rain, obviously. So it's an algorithm to find the convective cells in them. This is important because we want to use what we learn for convection parametrization. Right? This is very much, all I'm going to show you now is very much focused on what can we learn about convection parametrization. And remember, convection parametrization is about what is the statistical distribution of convective clouds in this grid box, and how is that statistical distribution interacting with the large-scale state of the atmosphere, right? So because parametrization is what we know the large-scale state, we would like to say something about the small-scale state. So we need to know both at the same time. Yeah. Okay. We use a 0 dBz threshold to say where's the top of the echo. So if we find a convective pixel, we go up and up and up and up and up, and where the reflectivity hits 0 dBz, we say that's the top. And it's not quite the cloud top. We know that's roughly one kilometer below the actual cloud top, often, but it's the top of the echo that we are using here. We're using it as synonymous with cloud top. So if I say cloud top, you know I actually mean echo top, right? So that's fine. And we can also track these features. There are algorithms to this. Mostly in what I'm going to show you, we use 3 years of data, but we now have 16 years of data of well-calibrated radar data every 10 minutes. Okay, so let me show you a few things we did with this and what we also have large-scale data. Oh, my equation went wrong. Okay, we also have large-scale data, which we construct by using sort of borrowing from data assimilation, something called a one-dimensional variational analysis, where we use reanalyses or operational analysis from ECMWF. But we can't, it turns out in the tropics, operational analyses and even reanalyses aren't very good for some of the things that we are interested in. In particular, they're not very good for divergent wind. And as a consequence, they're not very good for vertical motion. So if you're using reanalyses in your research for the tropics, be very, very careful. Here's evidence for what I'm saying. We had a field study in Darwin in 2006. You can read all this up in a paper by Laura Davis and others in 2013. We had a field study in Darwin where we deployed a radiosonde array, 6 radiosondes in an array. Here's the array, 1 radiosonde in the middle, 5 around Darwin. And for 3 weeks, we launched sondes every 3 hours. So one of the highest time frequency experiments you can find, actually. And from those, doing an analysis, you can derive what the vertical motion is. Okay? And this is the vertical motion. This is the days of the field study. Blue is upward motion, red is downward motion, and this is the evolution of vertical motion from the field study. Now, if you take the operational analysis from ECMWF, then this is what you get. Okay? So you can see qualitatively there is some resemblance to the one we get from the observations, but quantitatively it's actually quite bad. In particular, it doesn't capture these subsiding periods very well, and it doesn't capture this late period, the ascent in the late period very well. So what we do is we perform an additional analysis, variational analysis, where we take grid points from EC by WF and pretend that they are radiosols. And then we mix them with other observations that we have, in particular the radar observations of rainfall, which we have available. We stick all that into variational analysis, and then the result is this at the bottom here. And while it's not perfect, this is much closer to the field study than this. So then, because we have radar information continuously for many years, we can construct this bottom data set even when we don't have radioson observations in this ring. So we use that, and that's what determines our large scale, right? So when I show you large scale information, that's where it comes from. Okay, so here's the first fascinating result, and very important for what comes this afternoon when I talk about parametrization and new ideas for parametrization. This graph shows on the horizontal axis simply the convective rain rate. So this is derived by, we look at all the pixels that have been classified by this classification algorithm as convection. Okay? We just work out how much rain on an average over the box comes from convective pixels. And that's the horizontal axis. And it's in millimeters per hour, so you can see it's sort of between 0.2 to the maximum is about 2 millimeters an hour or something like that. Multiply this is 24. That's 50 millimeters an hour. It's 50 millimeters a day. It's not a lot, but that's the contribution from convection over the grid walls, right? And as I told you before, that's actually, convection can't make all that much rain by itself. And the y-axis is how much of the area is actually covered by convection. So it's the convective area fraction. So it's the area these convective pixels cover divided by the total area. So the first thing, remembering yesterday's lecture, is the good news is that area fraction generally is quite small. 2%, 3%. So remember in parametrization we are assuming that the area fraction is small. So the good news is, for grid boxes, this is for about 150 by 150 kilometer area. This is what this is valid for. So for 150 kilometer grid boxes, the assumption that the convective area is small turns out to be a good assumption. That's right. So obviously as you go to smaller and smaller boxes, it won't be anymore. But the fascinating thing, and it really fascinated me, is that there's an almost one-to-one relationship between the two. So that tells you, if you want to, for nature to increase the area average convective rainfall, not the local rainfall, but the area average convective rainfall, right? It actually increases the area that's raining, not the intensity with which it's raining. That's not obvious at all why that would happen, but that's what happens, actually, right? So the area is what's driving the area average rainfall. What does it mean for convection parametrization? Well, it means that maybe predicting the area as part of our convective parametrization is a good approach, because if we know the area, we know most of the story, right? Because the area is setting the rain, and the rain is setting the heating, so which is what we want to predict. So area is becoming a very interesting variable.
Can you just repeat? Because, so area, when convective area fraction is increasing, convective rain rate also is increasing. Right?
Yes.
That's what you are saying.
Yes.
So rain rate is increasing means intensity is increasing. Right?
No, not at all. This is the area average convective rain.
Oh, it's area average convective.
Yeah. So it's not the local convective rain. We'll come back to intensity. I think I have a graph in here. If not, I can show you offline.
So it does not say anything about intensity.
No. Well, this is a combination of area and intensity, right? Because it's the mean over the whole box. But this is just the area. And what all we are saying is the main factor that controls the mean convective rainfall in the box, which is what you're trying to predict with your parametrization, is entirely controlled by the area, not by the intensity. Alright, so it's much more important to predict the area well than it is to predict the intensity well. If you can predict the area well, you have most of the information that you need. Alright, so that's kind of important. Oh, hang on, I want to go back. Now, just an aside story, because it's always fun. Yeah.
So in the higher side there is a lot of spread. In the
Yes.
lower side it looks like only nearly, but
Yes.
if you look at more than one.
Yes. We'll come, I'll show you more in a second. Yes, there is some spread, and it almost looks. If you're really optimistic, you can almost see two branches, right? One goes this way, one goes that. However, remember, there's thousands and thousands of points in there. So once you can see the points, like here, this is a very, very small subset of what we're seeing. So whether we trust this statistically or not is something you and I can have a conversation about, right? I don't think this is we shouldn't make too much of an interpretation of this bit here. But it is true that the spread is increasing as the rain is increasing. But we also have very little data now at that point because we don't have many very intense events. A fun story is we thought we had discovered this from data anyway, until I found a paper in the 1970s where people had used radar data to look at weather modification over the US, and they wanted to know what the area average rainfall is. So the key thing here is it's about the area average rainfall. Right? And in those days, in the 70s, radars were pretty new, and they didn't have relationship between reflectivity and rainfall. But they wanted to know what the area average rainfall was, and they found that if you knew the area, you had a very good first guess on the area average rainfall. You didn't really even need to know the variations in intensity. The area is what set the mean rainfall. They compared that to. So we weren't the first ones to discover it, sadly. We thought we were. We even said in the paper we were, but we weren't. We were lying to you. So if you do the same exercise for 16 years of data, so now the left-hand side shows it's the same graph, but lots more points, millions now. This is the main average rain. This is convective area fraction. You see we go a bit higher now. We go a bit higher in the rainfall simply because we have 16 years of data. The samples have become bigger. The colors here are the reflectivity, but don't worry too much. The colors here is how many points fall in which group. So you can see most of the population is actually down here in the weaker domain average rainfall and in the small area fractions, right? Then as you come out here, again you see this spread increasing, and you can almost convince yourself there may be two branches. But again, I would be very careful because there's not many data points out there. Okay. Now, coming back to the rainfall intensity, since I was asked. So the next thing we discovered is that my next question is what controls this convective area fraction, or what is it related to, right? So this graph shows you the moisture convergence on the x-axis into our grid box, and the convective precipitation area. So this is the area fraction. And then on the bottom it shows you K versus the convective precipitation area fraction. And what we see, K is not much related at all to this convective area fraction. So using K to predict how much it's going to rain in a box is a bad idea. And yet everybody is using K in their convection schemes. Right? It doesn't look like a terribly good idea. Because from an area average point of view, the relationship to moisture convergence is much stronger. It's not perfect, of course, but it's much stronger than it is to K. If we are interested in the rainfall intensity, so this is now rainfall only at the points where it's raining, not area average. We can see that the relationship to moisture convergence is not that great, and we start to see a little bit of a relationship to K, but not much either. You really have to squint. But the intensity is at least somewhat controlled by K. So the instability, one of the conclusions you can draw from this, the instability of the atmosphere sets how much it can rain per square meter. Right? In a square meter of rain, how much I get depends on how unstable the atmosphere is. But how many square meters are raining, which is much more important for the area average, is not controlled by the instability, but it's much more to do with the large-scale circulation. We use moisture convergence here. As I'll show you later, it turns out you can use just convergence. An even better relationship can be constructed if we use humidity as an additional predictor. So instead of just using convergence or K, we add a second predictor, which is humidity. Alright. If we do that, then we can classify, and this time we use another location, but let's focus on Darwin, and let's start at the bottom here. So this is a two-dimensional histogram now of the area fraction of convection on the left here, and you can see the numbers here. It goes up as you go to the reds. The x-axis is a normalized vertical velocity, i.e. convergence measure. So vertical velocity in the middle troposphere tells you how much convergence did I have below that level, basically. Okay, so we use 600 hectopascal vertical velocity. And this one is 600 hectopascal relative humidity. And it's flipped. So up is dry and down is wet. Okay, so it's an indicator of dryness, not an indicator of wetness. So it's an indicator of dryness. And it's also normalized. So the normalization, don't worry too much. And what you can see is that you get this relationship where if the atmosphere is moist and ascending, you get large area fraction. And if the atmosphere is dry and descending, you get very small to no area fraction at all. So convection relates to both of these variables. The most fascinating thing is you can look at, so this is the mean relationship. And here we look at in each of the bins, what is the standard deviation of area fraction in each of those classes. And the thing is that when the largest standard deviations, and this is in percent of the mean, the largest standard deviations in the relative sense are found when the atmosphere is dry and subsiding. And the smallest standard deviations are found when we have the largest area fractions, actually. So what we conclude from that, there's a discussion on how stochastic is convection, how stochastic is the relationship between the large scale and the convection, and how would we represent this in a model. And a lot of people have stochastic physics in their models that multiplies the tendency from convection and other parametrizations with a random number. Okay? But that means if the tendency is large, the noise will also be large. And if the tendency is small, the noise will also be small. Well, that's not what we're observing. We're observing that when convection is weak, the noise should be large. But when convection is strong, the noise should be small. Now this makes a lot of intuitive sense. Because if you're a forecaster, any of you have ever had the joy of trying to forecast rainfall in the tropics? You're probably all theoreticians like myself, but I've spent a lot of time in Darwin sitting next to forecasters. When there's a large-scale feature, like a trough or a cyclone or something, it's very easy, or depression or something, it's very easy to predict rainfall. Because it's going to rain a lot. It's very simple. But if there's sort of weak forcing and not much happening synoptically, they have no idea what's going to happen to the rainfall. And it's really, really hard to predict rainfall in that situation. And that's essentially what this is saying. It's saying when the forcing is weak, you can get a large range of area fractions of convection, and therefore convective rainfall. But when the forcing is very strong, the atmosphere is moist, the air is ascending, so you have synoptically strongly forced conditions like a monsoon trough or something, then the variations that you get are relatively small. Okay, so that's nice. If you use CAPE as your predictor, which is the top bit, suddenly the picture changes. A, the mean relationship isn't very good. We would have expected that because we saw that in our scatter diagram already. But also the noise is suddenly much more widespread. Right? So many more classes look very noisy. So now your problem looks extremely stochastic. Right? So if you use CAPE as your predictor and humidity, you get something that looks very, very stochastic. But if you use a different pair of predictors, it doesn't look that stochastic at all anymore. So the warning for those of you who work on stochastic physics, what you call stochastic depends on what your predictors are. Right? If you use the wrong predictors, it will be extremely stochastic. If you use good predictors, it may be less stochastic. So when we have this debate about how stochastic is convection, the first question we need to ask is, well, how are you trying to predict it? What is your mechanism of saying something about convection?
So the CAPE can still be, from your previous slide, CAPE can still be a good, I mean,
No.
I mean, CAPE can still be used as a trigger, but not as a closer, right?
Yes, you need the instability to
It
have
can serve
Yes.
some purpose.
Yes,
If
I agree. I agree. So and CapeMate is still a useful one, for instance, to calculate the vertical velocity in the clouds.
But not for closure.
But for closure, it's a difficult one to use because it's not really related to the area average.
Yes.
Okay. All right. A few more things we did with the radar. Forget the second graph. So using the SEPO radar, we found that there's actually 3 very distinct types of precipitating convection. This had not been reported before. And the third type is, I'll show you. And how did we find this? We found this by plotting the PDF of reflectivity at 2.5 kilometers in the atmosphere, which is the x-axis here. That's just reflectivity, and the colors are just the PDF, as a function of how deep the clouds are. Okay, so the y-axis is the cloud top height, the maximum height of the cell. So we collect all the cells that have a 5 kilometer cloud top height, say, and we make a PDF of reflectivity from all those cells at 2.5 kilometers. Then we collect all the cells that are 10 kilometers, and we make a PDF of reflectivity at 2.5 kilometers. And that's what's shown. And so what do we see? Well, what we see is as we go up in the atmosphere, as the cloud top increases from 3 kilometers all the way to 7 kilometers, the mean reflectivity at 2 kilometers increases. Okay? So the black and the white line are the mean and the median of this PDF. Okay? So they increase. And at about 7 kilometers or so, this increase stops. And then, whilst the left side of the PDF you can see is still changing, the right side is constant and the mean and the median are constant. So we have this regime where as the clouds get deeper and deeper, the rainfall at the surface doesn't change much anymore. So what this means is here, the rainfall is increasing as the clouds get deeper and deeper and deeper. Then there's a regime where actually this stops happening. The clouds are deeper and deeper and deeper, but the rainfall that comes out at the bottom isn't all that different anymore. And then only when you get to about 15 kilometers, you start seeing a massive change again, where you get this increase. So really there's 3 types of precipitating convection. If we translate that into precipitation, which we can with using a relationship between reflectivity and precipitation, this is now the rain rate at 2.5 kilometers. And again, we see the same thing with the median rain rate. The median rain rate is increasing until the clouds are about 7 kilometers thick. Then it's a pretty constant, and then it's dramatically different. So, and this is rain over a 10-minute interval, right? So this is instantaneous, as close to instantaneous rain rate as you would get. And so, one of the conclusions is that we need 3 types of convection, precipitating convection. One is we call the congestus phase, congestus type clouds, that are the ones that go up to about 7 kilometers. Between 7 and 15 kilometer top we will call deep from now on, so traditional deep convection. And then we have an overshooting type of convection, which seems to be very important, not only to make exchange between the troposphere and stratosphere happen, but also because it produces the most extreme instantaneous rainfall. So all that really heavy instantaneous rainfall comes from this overshooting convection. Now the next thing we can ask is, what is the relative humidity in the atmosphere, the profile of relative humidity in the atmosphere, as a function of how deep the clouds are? Okay, and so initially we start with clouds that are 5 kilometers deep, and you see the relative humidity is this black line, and it's very dry. The atmosphere is very dry. So that you would expect. When the atmosphere is very dry, the clouds don't go very deep, they can't roll because of this entrainment process. Fine. Then we go about 11 kilometers, and 40 to 11 kilometers we get the blue line, and so when the clouds are very deep, the atmosphere is very moist. Right? That's not very surprising. But now comes a big surprise. If we go for even deeper clouds, the atmosphere gets drier again. So the deepest clouds do not occur in the moistest atmosphere, actually. They occur in a relatively dry atmosphere. The explanation for that is that you need to accumulate some CAPE. You need to get this very high intensity rainfall, actually. And to do that, you need to prevent convection from being able to pop up anywhere you like. If you look in a bit more detail, you find that these things often happen when the atmosphere is slightly suppressed, not If it's completely suppressed, you don't get any convection. If it's completely ascending, you're in the monsoon, you get the blue stuff, and you don't get very deep convection, because convection happens everywhere. It just pops up everywhere and it doesn't go very deep. But in between, where it's sort of, you could have convection, but you need to push very hard, and you need to heat. You need extra processes, often land sea breezes are the process in the Darwin region that make it happen. Then you get the really intense convection, but not a lot of it, just in a very small area. But it goes really, really deep and rains really, really hard. And that's when it's dry. So again, you have to keep in mind for parametrization, if you want to make something function of humidity, it's not, the relationship is not trivial to humidity. You know, there are states of convection where the atmosphere is relatively dry and yet it rains a lot. So a simple relationship in saying, oh, the moister it is, the more rain I will make, is not necessarily going to work. Okay, I'm going to skip over some of this because we won't have enough time. Yeah, I'm going to skip over this. Oh, so one thing we found is when we group this, well, actually, I'm not going to stupid. All I wanted to say is we then did an event-based analysis to try and find out a little bit more about how this area fraction growth works and how the intensity growth works and what are the clouds that are involved in this growth. So we define rainfall events. So we find the maximum rain rate, and then we trace them backwards and forwards in time. And we group this into two classes of events. The events where it rains a lot in the morning, and you can see that in Darwin, when it rains a lot in the morning, it rains over the ocean. It's not, that's pretty typical. Whereas when it rains a lot in the afternoon, it actually rains over land. So there's this diurnal cycle. So we wanted to separate those two classes, look at them separately. And here's a picture of the number of cells at a particular number of convective cells at a particular height. The height is here, the maximum height of the cell is here. How many cells of what height do we find around these rainfall events? And that's, if you start with all the events at the top, you can see that there's a lot of cells that are shallow initially, not many deep cells, and then a few hours before the peak rainfall, the convection goes deep. One of the things to note, which is important for parametrization again, is that even when we have at the rainfall peak, which is here at time 0, we have lots of deep clouds, but we still have an enormous amount of shallow clouds as well. So there's a coexistence of shallow clouds and deep clouds, even at the time of the rainfall peak. Okay? Modern, as I told you yesterday, parametrization schemes can't deal with that. They either have deep or they have shallow. They can't have both at this point in time. So I'll show you this afternoon how we intend to change that. But it's important to look at this. Just for fun, we then composited the number of cells, the size of the cells, which is this sort of convective cloud area, and the rain intensity around this rainfall peak, right? So what you see is, here's the peak. The cell number, as you approach the peak, you get more and more convective cells. The area of the cells also goes up, so this area fraction goes up, this is the number, and then it peaks and then it goes down. So a lot of this peak and decay is to do with how many cells you have precipitating in your region. Okay. The intensity, on the other hand, is the red line, actually doesn't peak when the mean rainfall peaks, it peaks before. So the mean rainfall peaks after you had the highest intensity of the rainfall, because you're still generating more cells. So again, it shows you the importance of this convective cloud area versus the intensity. We then tracked cells because you can argue, well, when we say there's a cloud top at 5 kilometers or 7 kilometers, maybe that's just a cloud that is still growing. And it's actually not stopping at 7 kilometers. It's just we have a snapshot, and the snapshot has a cloud at 7 kilometers, but that doesn't mean the cloud will stay at 7 kilometers. It could be a cloud that goes to 15 kilometers, which right now it happens to be at 7 kilometers. The only way you can find out about this is by tracking the cells and finding out how deep they ultimately go. And then what we find here is that to get, well, this is a complicated plot to explain. I just give you the upshot. We see the congestus clouds. These are the clouds that never grow deep, right? So these are clouds that always stay congestus. And the dashed lines are the deep clouds. And then what we sort them by here is by convergence into the region. Okay, so this is again, this is the onset of an event, hours before and after, and we look at congestus clouds and the deep clouds, and what we see, and then we sort them by convergence. This is strong convergence, medium convergence, weak convergence, low convergence, effectively. And what we see, the congestus clouds don't care whether there's convergence. All three curves lie on top of each other. But the deep clouds, they care a lot. And you only get lots of deep clouds if you have convergence into the grid center. Alright, so again, this is a confirmation that the deep clouds are very strongly coupled to the dynamical processes in the atmosphere. Whereas the shallower clouds, they really are more thermodynamic entities. They don't really need large-scale influence. Finally, we are also able to estimate the vertical velocity. Remember, the mass flux is a product of area fraction, which we just showed you we can derive from radars, and velocity. So if we wanted to know the mass flux from observations, which would be really cool if we could do that, we would have to have estimates of velocity. All right. We are able to get these estimates of velocity from a wind profiler pair. Two different frequency wind profilers are deployed at Darwin. And the cool thing is one of the profilers sees, the difficulty with a single profiler of doing this is that you have two motions that you can see. One is the air motion, and one is the motion of the hydrometeors. And you need to separate the two from each other. And to do that, you have one instrument here that sees both the air motion and the motion of the hydrometeors, and one that sees only one, which is only the motion of the hydrometeors. And by using them both, you can figure out what the air motion must be. And here's an example for what you get. So this is an estimate of vertical velocity as a score line passes the wind profiler side. And you can see here comes the score line. They get maximum vertical velocities of 10 to 15 meters per second. It's tilted, so that, and then behind there's the stratiform region where you get weak vertical motion. So that's the sort of data that we can derive. We even know how much we can trust the data. Down here is an error estimate, basically. Now, if we do that for the Darwin region, we can actually derive mass fluxes. And someone asked me yesterday, what's the mass flux profile look like? Well, here's the mean mass flux profile for the Darwin site for 3 years, derived from these wind profiler combined with the radar. And you can see it peaks. We can't really go below 2 kilometers because we don't have the radar information below that. But above 2 kilometers, there's a peak at about 5 to 6 kilometers. The solid line here is the updrafts, and the dashed line is the downdraft. So because we know whether the air is going up or down, we can actually identify both up and downdrafts. And these are the area fractions as a function of height for updrafts and downdrafts. Once you have that, you can ask the question, well, again, how does the large scale influence the mass flux? Which again is the parametrization question, right? So how is the large scale atmosphere controlling or influencing what we observe? So here we look at 4 variables in the large scale. One is humidity, one is K, one is sin, which is this inhibition of convection low down, and one is the vertical motion at 500. We show 3 variables. This is the mass flux, this is the area fraction, and this is the velocity. Remember, fraction times velocity times density is what gives you the mass flux, so they are related. And the gray is always the mean. So if you take all the cases that we have, that's the mean mass flux, mean area fraction as a function of height, and mean velocity as a function of height. And then what we do is we divide the data set into terciles. So we take the moistest third, the driest third, and the middle third we don't show. So this is the moist third, is the dashed line, the dry third is the solid line. So what do we see? When the atmosphere is moist, the mass flux is larger than when the atmosphere is dry. Okay, that we may buy. We also, but what's interesting about this is actually there's compensating effects between the area and the velocity with moisture. So as the atmosphere gets moister, the area fraction goes up, right? So more of the area is convecting. That's not that we would expect. But the vertical velocity has the opposite. So the vertical velocity is weaker when the atmosphere is moist than when it's dry. And again, it's the same explanation as we talked about before. When it's moist, convection can pop up everywhere. So lots of clouds will form, but each of them will be relatively weak. Whereas when the atmosphere is dry, convection cannot randomly pop up. It actually needs some focus like a sea breeze. But when it pops up, it's very strong. So the area is smaller, but the velocity is larger. K, on the other hand, you can see there's very little influence on the mass flux from K. There's a little bit, as we discussed. So strong K, the mass flux is a bit larger than weak K, but not nearly as much as we saw here, for instance, and we'll see below. The area fraction is only very has only a very small influence on Cape as well. You can see that the area is actually smaller when the Cape is strong. So that, again, I think that has to do with that the large instability means there hasn't been convection for a while, and convection cannot freely pop up anywhere at once. So therefore, you create large Cape. But the velocity now has the expected signal, and the velocity is related to the intensity of the convection, of course. So large Cape means large velocity. So instability is controlling the intensity, but it's not controlling the area, and therefore it's not controlling the mass flux very strongly. And let's forget about, well, sin is really what you would expect. If the sin is weak, you get lots of convection. If the sin is strong, you don't get much convection. It doesn't influence the vertical velocity much, but it influences the existence of convection very much, basically. So sin is something you need to pay attention to in your trigger function. And then vertical velocity is even more extreme than sin. If the vertical velocity is upward, you get mass flux. If it's not, you don't. It's a really separator of is there convection or isn't there convection. Okay. This is how much of this mass flux comes from each of the types of convection that we have identified. It's just for completeness. So if you look at the overall mass flux here, then the congestus clouds contribute this bit, the deep clouds contribute this dotted line, and the overshooting clouds contribute the dashed line. So they each contribute to this picture in different ways. We can see, for instance, if you look at vertical velocity, in the congestus, the vertical velocity is almost constant with height and it's weak. And the strongest vertical velocities we find in this overshooting type of convection, which is also what we would expect, right? That's the strongest convection that you can imagine. All right. Yeah, I'm going to skip over those. Oh, actually, it's the last two slides. Do you want to do the last two slides? Yeah. All right, we might as well. We're going to be a little 5 minutes over. That's okay. So the next question we had is, wouldn't it be cool if we could do this mass flux derivation from a single radar, where we don't need these wind profilers and so on and so forth? And what we found is that indeed it's possible to do that, and that we can construct a statistical model of vertical velocity. And what we did is, go back to this figure, we say we have three types of clouds, congestus, deep, and overshooting. And each of them has a very distinct profile of vertical velocity. So we make a statistical model, just a regression model for that profile. We just make it smoothed and make a function that describes the shape of this profile. So we have three functions, three shapes of profiles. Okay, that's very easy. Then from the radar, from a single radar, we can work out how many cells of each type we have and what area they cover, right? We only need a single radar to do that. So then the only thing that's left is, so that means we want 5 of those, 10 of those, and 2 of those, and that will become our mean over the grid points. But what we don't know yet is how strong should we make the vertical velocity? Because this is the mean, there's obviously variability around that mean, right? So we need to say at what point do we expect it to be very strong and when is it very weak? And here's what we found. To check this out, what we found is that if we take the weakest congestus and that's 20 cases of it. And the strongest congestors in our data set, weakest congestor cells and the strongest congestor cells, and we plot their reflectivity. So this is the x-axis is reflectivity, the y-axis is height, and the colors are the frequency of occurrence in that data set of certain reflectivities. If you take the difference, you can see that when the congestus is strong, the reflectivity is increased, which is perhaps not surprising. But it's increased quite homogeneously over the lower part of the cloud. Yeah? So it's not just increase at one level, but it's a homogeneous increase over quite some depth. If you do that for the deep clouds, you take the weakest deep ones, the strongest deep ones, you do this difference, you get a very similar result, and you do it for the overshooting ones. Once again, you get a very similar result. So what we learn from this is that the column integrated reflectivity is a good predictor for whether the clouds are strong or weak. So we build a statistical model where the shape is determined by how deep the cloud is, the strength is determined by the vertically integrated reflectivity, and Bob's your uncle, and the number of clouds we can determine from the radar scan. So suddenly we can make a mass flux profile for a region from a single radar, which is quite remarkable because that means we can make it everywhere, anytime on Earth where there's a radar. We still need to confirm that our statistical model isn't just true and Darwin. We haven't done that yet, but if we could confirm that, then we can make it, we can find out what the mass flux is all over the world. We can even use trim data eventually to make a global picture of mass flux. And I think that would be great for evaluating convection schemes and climate models, right? If we had observations, or pseudo-observations of mass flux. So here's just an example of doing that for our field experiment. So what have we got here? We've got the domain average convective rain rate is the red line. The cape is the black line. And again, you see the relationship is pretty weak. You get large cape and weak rain, and low cape and large rain. And then this one is the convective area fraction as a function of height, which is observed by the radar. And this is the derived mass flux using our statistical model. And here we had three distinct periods in this experiment. We had a monsoon period, a suppressed period, and a monsoon break period. And these are the mass fluxes. So you see during the monsoon, the mass flux is the largest. When the monsoon is active. During the suppressed, it's the weakest, and the break period is somewhere in between. And this is just predicted with our simple statistical model. All right, so that's my quick run-through of how to use modern observations, both satellite and radar, to think more about cumulus parametrization. And I take any questions. Yes.
If you could go back to that slide where you showed the scatter plot between the convective area fraction and the area average rainfall.
Yes. Yeah.
So what I was wondering is that this one-to-one relationship, what you were saying, so this actually is mostly true when this convective area average rainfall is very small, right?
So the one-to-one is true even here. It's just the scatter around it gets larger, right?
So I was wondering if this plot, if instead of plotting the x-axis on a linear way, if it was plotted in the logarithmic way,
okay,
would the scatter be same or it will be more?
I don't know. I haven't done it. No, I agree that there is some scatter in that relationship, but it's still even at the high end, and particularly when you go to more data. At the high end, you can perhaps say there's a sort of leveling off here, right? So it's sort of non-linearly leveling off, and the area fraction is not increasing as the rainfall is increasing. We're getting into very small samples here. Look, where it's red, we have 10,000 samples in the bit where it's red, and we have 5 samples in the bits where it's blue. So we really can't trust those blue ones very much. That's the problem. Because we don't have many cases up here. But in this regime, up to about 1 millimeter per hour, I would say this looks pretty linear to me.
Sometimes actually it happens that even if it looks very linear, then because the values are small, if the axis is linear, but when
Yeah.
it is plotted in the logarithmic, there
Yeah.
will be some more scattered.
Yeah, that's a good idea. We should do that. Yeah, we'll do that. Okay?
Christian.
I'm not in charge.
What deviates the relationship between the large scale and the convective scale from being deterministic to stochastic?
What determines that? I have no idea. I think my sense is that if the convection is strongly dynamically coupled, and I specifically use the word coupled rather than forced. So if the convection is embedded in a synoptic or even smaller scale feature like mesoscale feature, right, like a sea breeze or something, then it becomes more deterministic because we know more where convection will occur and how strong it will be, because that's related to how much convergence you have into the region, for instance, which is a function of the strength of that dynamic feature. If you are, on the other hand, if you are in a sort of weakly forced or not, even between a high and a low, and there's nothing going on. You're in the middle phase of the MJO. If you're in the active phase of the MJO, so that MJO is a good example. If you're in an active phase of an MJO, you kind of know you're going to get a lot of convection, and it's pretty deterministic, right? Because there's this large-scale feature called the MJO right above. If you're in a suppressed phase of the MJO, you know pretty much you're going to have no convection, right? Because the atmosphere is suppressed. But if you're in this sort of in-between phases, it's really hard to know, are you going to get a lot of rain today, or are you not going to get a lot of rain today? And I think that's what sets it. So if where the convection is dynamically strongly coupled, it's deterministic. And where it's weakly coupled to the dynamics, it's stochastic, it's more stochastic. That's my interpretation of these results, basically. And the reason it's important is if you build a stochastic parametrization, then you want to take this into account. You don't want to perturb your convection when you think you can predict it well, because then it's likely that your model is making a small error at that time. But it might make a big error when it's not so predictable.
So, from your answer, if you go back to the previous slide, so the relationship, the bulging of those data points, can you please say the deterministic relationship and the scatter is due to the
Yes.
stochastic?
Yes. And the key thing here is to remember that the scatter, and it's a bit difficult to see, as the numbers get bigger, right? This is a purely statistical artifact. The scatter will go up as the numbers get bigger. Of course it will, because the numbers get bigger. So, right? But if you do it in percent of the mean, the scatter goes down. Actually, as you go from here to there, I haven't done it for this curve, but it's essentially what we've done here. These numbers are percent of the mean, right? Because as the numbers go up, if you didn't do this in percent, the standard deviation goes up. I have another graph there's a graph in a paper that we wrote where that's in there. As the mean rainfall goes up, the standard deviation of rainfall also goes up. But that's just because the numbers go up. But if you do the standard deviation divided by the mean, that goes actually down. So the relative scatter around your mean goes down. Right? So that's the key thing, which I think is a sign of it becoming more deterministic as it gets stronger.
So, as you showed the convective area fraction, so convective area fraction has one-to-one relation with the convergence motion convergence, but not with gate. So from that, can we conclude that the area covered by the convective layer is driven more by the large-scale dynamics than
Yes.
the local dynamics?
Yes,
Local thermodynamics.
it's a really interesting question. If you really want to have a good science problem, I don't understand why nature does it this way wrong. because there's a priori why would the area increase as the mean rainfall increases, right? Could be the intensity increasing. So why isn't that the case? It's a really good question. I think with the convergence you have to be careful. I will show you, I think I have it in the afternoon talk. Yeah, I'll show you in the afternoon. If you do a lag relationship between rainfall and vertical motion, a lag correlation, it actually peaks before the rainfall peak. In other words, convection is leading the vertical motion. So one of the big difficulties with all of this is that it's a coupled system. So the convection is coupled to the dynamics. It's not one driving the other. They are coupled. So you might get convection somewhere that may lead to convergence, which leads to more convection, which leads to more convergence. In other occasions, you may have convergence, like in a sea breeze. That gets you convection, which then strengthens convergence. So it's not always one leading the other, leading the other, leading the other. However, as I'll show you this afternoon, even though the highest correlation between vertical motion and convection seems to suggest convection leads the vertical motion, at time zero, the highest correlation of any variable with convection is coming from vertical motion by a long way. So if you're a mathematician and you look at this and says, what's the best predictor I could use at time zero, at time now, to say something about convection now, it's by far and beyond the vertical motion. And I will use that this afternoon to build a new convection scheme.
One more question. Initially you mentioned as temperature will increase, organized convection will increase.
Well, there's an indication that may be
What
true.
is the theory behind it?
There is no theory really, and it might not even be. Remember, correlation doesn't mean there is a physical relationship. It could be that both happen at the same time for completely different reasons. So the world gets warmer and the organized convection gets more frequent, but they may have nothing to do with each other. It just may be completely coincidence. There are a few papers that look at, but I will show you probably tomorrow afternoon in my talk. There are a few papers that look at convective radiative equilibrium, and they look at very small domains, and they run cloud resolving models, and when they increase the sea surface temperature in these simulations, the degree of organization goes up. So that's the theory behind this. It turns out that these simulations are complete rubbish because they assume they use way too small a domain to assume. You can't assume convective radiative equilibrium on such a small domain, but they do. And so there's a big question mark around their results, actually, what they mean, if they mean anything for the real world. So I don't think we understand it. It's at this point in time, it's just an intriguing relationship that we don't understand.
These wavelets that you have shown, is it the mean of the instantaneous wavelets or is the mean of the accumulated rate?
It's instantaneous.
Every time you have
Every
snaps,
10 minutes.
You have the snaps and then you take the average.
Yes, you take a 10-minute snapshot and you take the average over the area.
Okay. So in one of the plots you showed like when the cloud head is increasing at lower levels, the rate increases, and in the middle it is kind of becomes constant, and in the upper level again it shoots up.
Yeah, this
That's
one.
plot. So is it related to the fact that until you reach a particular height where you hit a stable layer and form a lot of stratiform rain, until it will remain constant in the middle?
There is no stratiform rain in this.
So this is all convective.
This is all convective rain. So all that is saying is that as as the clouds get deeper, when they are little, as they get deeper, they rain more. Okay, that's fine. But then for some reason, once they get to about once they get to about 7 or 8 kilometers, as they go deeper, they don't rain more anymore. So they have sort of settled on some sort of rain rate that seems to be independent of how deep the cloud gets now. That does make some sense actually, because if nothing else changes, once you go to 8-9 kilometers, the condensation isn't adding all that much water anymore, right? But once you get very deep clouds, you get these very large rain waves, and that has to do with the fact that the vertical velocities are much stronger in those clouds. So most of that rain, even that rain, is produced in the lower parts of the clouds, because that's where all the moisture is. But it's done by having much stronger vertical velocities, and potentially, yeah. Well, we don't know anything about area because we do this pixel by pixel. So it's really much stronger vertical velocity, which is also what we saw later, right? That the overshooting type had much higher vertical velocity than the deep type, basically. So it's the vertical velocity that's driving this.
You also mentioned in one of the points like the deepest clouds appear in dry environment.
Yes.
So can we expect that during break-like conditions or
Yes.
extreme events, what happens? This all happens during break period, large-scale break period.
Yes. So now, yes, I think the answer is yes, but you have to be careful what you call an extreme, right? So when I say extreme here, this is extreme instantaneous rainfall. Not necessarily extreme rainfall in an area average sense, or even after averaging over an hour, it may not be extreme anymore. This is extreme in extreme intensity, right? So it's different from what people call extreme rainfall. So it will be interesting to see, and we are starting studies of that, is how much, if you made hourly extreme or 6-hourly extreme rainfall at a point, how much of that is still coming from these clouds? How much is coming from stratiform, which is in India? So that's all open questions. We don't know.
Okay. So, I mean, what I was just wondering, what is your, take-home message from this lecture? That see what we in the last 2 days what we discussed. So, should we think that the mass flux is an innocent guy? He has no. It's not to be blamed. But the way we are incorporating the mass flux in the parametrization is to be blamed. That is, can we say that? Or you feel that as we have seen that, the CAPE is not doing a great job in closure,
Yeah.
but serving some purpose weakly in trigger.
Yes.
So if we still hang on with the mass flux
Yes.
and CAPE,
Yes.
these two uncertainty gives us the chance to add stochastic parameterization at these 2 points. Or
Well,
what?
I think the mass flux is too blunt an instrument, is my conclusion from this.
Okay.
So if you think about a take-home message, mass flux is the product of area and velocity. What we've seen is that one large-scale variable, stability, one large-scale set of variables, those related to stability, control the intensity. So CAPE controls the intensity. Intensity is related to velocity. So one part of the mass flux is related to CAPE. The area, on the other hand, is not related to CAPE, but it's related to convergence, vertical motion. So another part of the mass flux is related to convergence. This is probably why, when you use convergence closures in mass flux schemes, they sort of work and they sort of don't work. If you use CAPE closures, they sort of work and they sort of don't work, because bits of the mass flux are related to either of those two, right? But basically, the mass flux is too blunt an instrument, and you shouldn't use it anymore. Instead, what we should do is we should split up the two into velocity and area, and then we should have the area parameterized as a function of the large-scale flow, omega, for instance, and the intensity should be parameterized, which it already is, because we're doing an ascent into an unstable atmosphere. So the intensity, the vertical velocity, should be parameterized as a function of k, and then we get the right answer.
In a bulk scheme, you can't do that, right?
Yes, you can.
Velocity and
Yeah, you can. You can have a bulk, just one velocity in one area. You can do that if you want. So I think that's what we should do. And I'll show you this afternoon. And it has other advantages, as we will see this afternoon. Many of the things that we don't like about our current convection schemes could be conceptually, and I don't know whether that's practically possible, but conceptually can be resolved also by separating area and velocity and not lumping them together. So, the mass flux is to blame. The mass flux isn't innocent.
I see. Any other questions? As you can thank.
Alright, so it's not quite lunchtime yet, but soon.